All right. So, yep. Oh, that I uploaded. Okay, I'll go in and change that this afternoon. I was working on that this morning for all my classes, so I didn't have a chance to like look over to make sure there was no issues. But the 17th, you said?
Yes.
Okay.
The one that you just put in.
Okay. I'll that should be updated this afternoon. Thank you. Thank you. All right. So we've got 2 Excel files up on Canvas that we'll work through today. Just a little bit more linear regression, kind of thinking about how, the types of questions and topics we could tackle. I don't think I have anything else at this point to mention. Yesterday I did put up that 4th Excel assignment. So this is just more linear regression. We'll actually use one of the data sets to start today that you'll be using for that homework. So kind of being able to see that should hopefully help make this a fairly easy one. And I was just told that there's an issue with this iPad uploaded, so I'll re-upload that this afternoon and try to get that fixed. But why is there nothing? So I've got this powerlifting, and I think it says small next to it. That should be up there on Canvas, as well as this in-class lawsuit. So this is the basically the same data that you'll have for that Excel 4. Okay. So I stumbled across this. I wanted to do something with like discrimination. It's kind of interesting to kind of work through a data set like this. And it was this data that was provided from a lawsuit that was in 1994. And I don't think they specified exactly what university it was, but there was like a medical school where they had, professors there who were also doctors. And the lawsuit was about gender discrimination, right? That the women at this medical school were less likely to kind of get promotions or tenure, and were getting paid lower salaries. So I kind of specifically made your Excel assignment, and I know a little bit about the results because I kind of worked through it to create it. But that's going to focus on salaries. Okay. So one thing that we could do, and that we haven't done as much of in class, is using a dependent variable that's 1, 0. Okay. So the question that I'm going to start out with is going to be something like, okay, we've got whether or not someone makes it. So I don't know how aware you are, but there's 3 levels of being a professor. So assistant professor, when you get hired in, then eventually if you get tenure, you get promoted to associate. And then if you kind of continue to do things that are good, eventually you get full, right? So there's like promotion levels. Okay? So this associate variable is just a 1, 0 if the person is an associate professor, or so 1 if they are, 0 if not. Right? So maybe we want to see what's the likelihood that at this university, someone became an associate professor, and we'll primarily focus on whether or not they're female, right? And then we have all these additional controls, which we'll take a look at. But really what this slope coefficient would tell me, once I come up with this estimate, we're going to start out, right, always assuming that our coefficients are 0. So that being female should have no impact on whether or not you get promoted, right? Like hopefully, hopefully that's true, right? Now, if we found an estimate that is negative here, that would tell us that relative to being a male, the female working here would be less likely, right, have a decrease in their probability of becoming an associate professor. Okay, so if we find a negative value and the p-value associated with that coefficient is less than, whatever level we want to set it to, and so alpha could be 0.1, 0.05, 0.01, then we could reject the null, which would mean that we can reject that there's no relationship between being female and being promoted to associate professor, or we're saying that there is a significant relationship, which would be a bad thing, right, for society. But, I don't know what the results will be yet, but we'll see if this is the case. Okay. So I've got all of this. Like I'll start out with a very naive kind of regression. So I'll go to data analysis. I'm going to do a regression. Hit OK. My y variable is going to be whether or not they get promoted to be an associate professor. So I'm just going to select that variable. Actually, I want to show you something I don't think I have yet. Let's say I just selected the data, right? So I'm not going to select the labels here. I'll show you what happens. And then I go, okay, my x variable, I want to look at what's the effect of whether or not the person is female. So I select that. So I haven't selected the labels. If I hit OK, notice it starts calling these x variable. Well, now if I've got 10 different variables in there. They're all X variable 1, X variable 2. It's hard to keep track of what's what. So that's why just in practice, I'm going to delete this. In practice, I think it's just always better when you're selecting the data. If you just select the, where is it, associate, select the label as well, right? That way, now when I run my regression, oh, where's the female variable? Now when I run this regression and I select labels, now it tells me what that X variable is, okay? So, zoom in here a little bit. It looks like we're not explaining a lot of the variation, whether or not someone gets promoted here, just 0.008, so 0.8% of the variation that we see in whether or not someone is promoted to associate or not is explained by their gender. So at least that's good. If I had a R squared here of like 0.9, that would be alarming. Right? I shouldn't be able to explain that much of your likelihood to get promoted by just your gender. Hopefully it's that R squared is very close to 0. However, if I look at the estimate, it does look like it's negative, right? So the way we would interpret this, we've got 1, 0 variables on either side here. So the 1 unit change in X, anytime we have an indicator or a dummy variable, it just means going from the 0 group to the 1 group. So if I was looking at a male, comparing to a male, if the individual was female, the likelihood they get promoted to associate would be predicted to be about 0.08 lower, right? Or an 8% less likely, right? Because when we have a 1, 0 variable as our Y variable, we said that our coefficients can be interpreted as like changes in probability, right? Because we can only go between 0 and 1. So being female relative to male decreases the probability someone gets promoted to associate professor by about 0.08. So this looks bad. Now the p-value is not quite significant, but here's something where, and this, I deal with this a lot more in what I do, and out there in the real world, maybe people aren't as sticklers on it, but like, okay, so I can't say that this is significantly different from 0, right? I can't reject the null at any of my conventional levels, right? But what is a level that I could reject this at? 85%. Is 85% confidence really that much worse than 90? I would argue no, right? Like this isn't highly significant, but it's still pretty strong evidence that there's some discrimination going on here, right? Now, I doubt the lawsuit stops here because this is pretty naive, right? What if, there are, differences between males and females in terms of all these other characteristics that make it more or less likely that you get promoted? We haven't controlled for anything, right? I haven't controlled for performance. I haven't controlled for experience, anything. So I go back and say, okay, that was a pretty naive regression. I'm going to include all these other controls, right? So I want to include whether or not the individual had a clinical emphasis, whether or not they were board certified, their publication rate, the number of years of experience they had. And I also want to include things like what type of medicine were they involved in. So here's what I'll show you a couple of things. When I organize this for your homework assignment, but it's going to have some issues for what I want to do here. So if I want to select all of these variables, I go to data and data analysis. And I say, okay, I want to use this as, so it's still my Y variable, that hasn't changed. But on X variable, I want to include all these indicators, hold control, as well as all of these, right? Hold shift, hit the down arrow. Well, I can't select all these columns at once unless they're right next to each other. And even if I do, like, so I can go put these in there, as well as, right, put these, so you kind of erase it. There's no way I can do that in Excel. So what I have to do is anytime I want to run a regression, I have to make sure that all the independent, all the right-hand side or all the X variables are right next to each other. Now, that's fairly easy because all I have to do is move things around. So I highlight that, kind of using this drop-down arrow, move it over here. And now all of my X variables are next to each other. So I'm also going to move these back here real quick. I'm just using that control shift to like go up and down real quick. So now I've got my associate, this is my dependent variable, and I've got all of the X variables I want here on the right-hand side. Okay. So I'm going to go to my data analysis tab. I'm going to select that associate variable as my dependent variable. And then my X variables are going to be everything from clinical all the way to that female indicator. Select that, all those columns. I've selected my labels, hit OK. Now notice something weird's happening, right? So this is another issue that we're going to have arise in Excel. So for some reason, that surgery variable looks like I've got zeros. Yeah.
Hey, you lost me when you took that whole chunk of things and moved it over.
Okay. Okay, so let's go back then. Maybe. Well, let me keep on doing. So what I did there was, if you select columns in Excel, all I did was select them so that I could move them over. So before, right, they were somewhere over here. So let me see if I can get back to what it looked like. These were the ones. I'm going to copy these. Insert copy cells. So it looked like this, right? So all I did there was select these cells. So if I go to the very top, notice how I get this like drop down little arrow. I selected from surgery to female. I then, if I get this like 4 arrow cursor, left click, I can drag this and just move this over. You could copy and paste it too if you wanted to, if that's easier. Yep. All right, so, and then I selected this and just moved it back so that we didn't have all these blank columns. Okay. So I ran that regression, but I have an issue, which is this surgery variable is like showing me zeros and I've got some hash, what's going on here? So I think this was the class that I did on Zoom on Thanksgiving. So I think it's a good time to go through this again based off of, I can see view counts on YouTube. So what issue, if anyone watched it, is arising here? So I've got all these indicators for what type of medicine the person was like teaching, right? So did they specialize in physiology, surgery, etc. So if I include, like, these are the only specializations they could have. So if I include all of those coefficients, what's the comparison group? So usually you would say if that doctor / professor was in biology, right, that this is the change in the predicted promotion to associate relative to what? Well, I had to leave one of the groups out, okay? Whenever I've got this indicator variable, so I'll actually show you a little more. So the original variable for this was only one variable, and it had like the words surgery, biology, genetics, right? It had their specialization. Well, I can't use a qualitative variable, so I have to create these indicators. So if I include an indicator for every single possible specialization, there's no comparison group, there's no base group. So I have to leave one of them out. So if it were me, I would probably, I'm just going to guess, I could be wrong. I'm guessing surgery has the highest likelihood of being promoted because it's, I think, usually attracts kind of the higher skilled doctors from everything I've read. So I'm going to move this out of the way because that's the variable that I want to exclude from my regression. Now, one thing you can do when you start moving things around is like copy and paste and create new worksheets that have like, well, this is the data format I needed to run this regression. This is the data format I needed to run this next regression, right? If I have you running like multiple regressions here. So I'm going to leave surgery over here and then go back. And now when I select my X variables, I'm just going to select these, right? Leave out that surgery variable, hit OK. And now I don't get any issues, right? Now, if I compare this, right? So 0.500, 0.500, these are the same values because Excel automatically dropped one of those. The problem is when it automatically drops one of these, it usually screws up the p-value on one of the other categories, right? That in this case for what their specialization was, okay? However, if I leave it out on my own, none of those p-values get screwed up. I can see all of them. So when you're having a group of indicator variables, right, that represent one thing, so this could be like car color. You would include every single color, but leave out maybe, is the car white, right? Leave out one of those so that you have a comparison group. So now when I left out surgery, the interpretation was if someone's working in the biology department relative to a surgery, probably they get promoted is about 0.04 higher. So I was actually wrong. It looks like all of these, you're more likely to get promoted to associate relative to if you were in surgery, right, or in that classification. So we've noticed we've included all these other control variables. We'll now look at what happens to kind of our female. It's still pretty close to the same, negative 0.08. It's a little less significant, but once again, I'm really close to 80% confidence here. That's not like the worst, right? I couldn't say with 90, 95, 99% confidence that there's a impact of being a female on promotion, right? I couldn't, right? I can't reject the null. And remember our null. Oh, I don't have this blown up. Our null is that there's no relationship or there's no effect. So I can't quite reject that, or I fail to reject it at my normal conventional levels, but the p-value of 0.2, it's not that high, or sorry, it's not that like high of a p-value. I could still almost say something with 80% confidence here. So more bad news, right? It's just not amazing evidence that there's discrimination, but pretty strong. Okay, so maybe it's that there isn't discrimination going on at promotion at like assistant to associate, but maybe from full, right, or associate to full professor, right? That final promotion. So let's go, and that's where you kind of see the biggest bump in pay, right? So if they're less likely to get promoted, they're also less likely to get this big bump in pay. Right? So now I'm going to do the exact same thing, but I'm going to use this full professor variable, which is a 1 if they get promoted to full professor, 0 if not. I'll then go to my data analysis, regression. Now I want this full variable, right? So did they get promoted to full professor or not? And just to double check, I want to make sure all my X variables are included here. Okay, so I'll select those. I had my labels. Now if I look at these results, first of all, I'm explaining about 35% of the variation that exists in getting promoted to full professor. Right? My R squared, I'd like it to be a little bit higher, but it's not terrible. Okay. I scroll down here and I look down at this female variable. Well, now I've got even worse news, right? So maybe I couldn't say that there was discrimination going on at high levels of significance or low levels of significance, high levels of confidence for being promoted to associate. But when I look at being promoted from associate to full, there's a pretty strong negative effect, right? Being female relative to male, holding all these other things constant decreases the probability of getting promoted to full professor by about 0.12 or about 12%. And my p-value of 0.03, this is significant at the 10 and 5% level, where I could say it with 90 and 95% confidence that there is a statistically significant relationship between being female and promotion to full professor. So they lost this lawsuit. So in 94, and then I gave you some of the data from salaries in 94 and salaries in 95. Some of the questions, I have you run regressions. Think about, did the result of this lawsuit have any impacts on salaries? Maybe even though we had promotion differences, maybe it doesn't play out in salaries as much. I don't know. You'll have to find out. But yeah, at least on promotion, it looks like there was a little bit of discrimination going on here. Now, think about how strong this regression result is, right? What I could say was, look, two people who either both have a clinical emphasis or both don't, both are board certified or they both aren't, both have the same exact publication rate, same years of experience, work in the same area or department, but one of them's female, one of them's male, that female's 12% less likely, right? Or has a probability of 0.12 less to be promoted to full professor. So pretty powerful, right? When we can start including like a lot of these control variables that we think matter in predicting our Y or our dependent variable. Okay. Now, there could be some other things that we don't have factored in here that maybe are correlated with them. So it's still a correlation, right? There is still how much? 65% of the variation in promotion that we're not capturing. So there could be an omitted variable bias still going on here. So we want to be careful, but it's pretty good evidence like that there is some discrimination going on. Okay. Any questions over anything here? So what do I want to think about? Anything else we could do be interesting here? I think we'll hold off. So I think I'll go to the other data set now, which was, I had all this powerlifting data. I don't remember why or how I found this, but I did. And it's got, I don't know, quite a few observations. 86,000, right? So actually, I'll pick on Cheyenne here real quick, but she was talking, Professor Nessa and I, and like the value of these big data sets, right? So you can see like here, I'm trying to give you a little bit of a sneak peek, like 86,000 observations. When you hear this term big data or data analytics, this is what they're talking about. They want you to be able to deal with data sets that are this large. And it's really not that hard. I mean, when we work through things like, I think initially I got a lot of emails when I was sending out some individual assignment data of like, this seems like way too much, seems like a lot. Well, really the principles of what we're doing, like with regression, I mean, we're going to go through the same steps if we have 1,000 or if we have 100,000 observations, right? I mean, in terms of like me selecting the column, it's the exact same thing. So, you know, dealing with the data shouldn't be that scary. In fact, the more variables and the more observations you have, like the more reliable your results are, right? So it's, you know, if you can do something with a data set of 100, you can do it with a data set of 100,000. Okay? You might need a better computer sometimes, but you know, you still should be able to apply the same principles. So I think this is another one where I was like interested. I think I showed you some stuff earlier with like distributions, like male and female strength. I've like just had this idea that like if you could take two individuals who had like the same body fat and like muscle fibers, there's no reason physiologically to believe that a male is any stronger, right? So it's really just all these differences like height and weight. And so I had this idea of like just to show kind of what that would be with this powerlifting data set. I've got the, you know, the way these powerlifting meets work, or there's 3 lifts, you get 3 attempts at each. And so then they record your best lift. So I just took the best squat, best bench, and best deadlift, and kind of added those up to see, okay, what was the total weight lifted by this individual, right, across these 3 different lifts. I then have kind of some of this other information over here. So I could do like a really naive regression and say, okay, let's look at this total weight lifted variable and see how is it impacted, or how well could I predict about whether or not the individual is male. All right, so I'll select that column, enter, okay. And unsurprisingly, when I don't account for anything, it's a pretty strong positive coefficient, right? Being male relative to female predicts that the weight total kilograms lifted is 275 higher, sorry. And it explains about 50% of the variation, right? Now, the reason why it's explaining 50% of the variation is because that variable of male is probably correlated with a lot of other things that matter, height, weight, right? So it's pretty naive because I'm omitting a lot of other important factors here, right? So go back to the data and think about, okay, what's even just one thing that should greatly impact it? Body weight, right? And probably age as well, okay? Now, age is going to be a weird one because if you go back far enough, there were probably fewer women involved in powerlifting 50 years ago as there are in the last 10 years, right? So all the older individuals in this data set, right, might be a higher percentage male, or we're not sure, right? It definitely seems like age could play a factor. So I'm going to go to my regression tool, and I'm just going to select body weight, age, and whether or not they were male. Okay. So I'm going to select that, hit OK. And now I can see if I look at that. Oh, I guess I have to blow this up a little more. Now it looks like that coefficient is a little bit smaller, right? It went from 250 to 190. So just these 2 variables, right, body weight and age, kind of bring that coefficient down closer to 0. Now it's still positive and it's still very significant, right? And I'm explaining about 65% of the variation, but there's probably a lot of other things that matter as well. So I could go back here and say, okay, look, I know that these matter, but I could also control for like, there's different categories, maybe throw in a squared term on age. Maybe I think it's not a linear relationship. And so if I go to my data tab, there we go. And I just kind of throw the kitchen sink, all the control variables I have at it. And I can't use that Wilks one. I'll explain why in a second, but hit OK. Now it looks like it's still about the same. So none of those really altered my results that much, although they did increase the R squared, so I can explain about 73% of the variation. So it looks like there's still a positive effect here, right? But as we already saw with like weight, once I included weight, it brought that down closer to 0. If I could include height, which I unfortunately don't have in this data set, it probably brings it down even closer to 0. If I can control for things like body fat percent, it probably brings it right. So this omitted variable bias, I think is kind of an interesting example. Given the data, I can't get this to be driven down. I would expect that as we add in more controls, that male coefficient starts to get closer and closer to 0, right? But it is, I don't know, something that I thought was an interesting example, like, or how we could start to identify like differences and really think about, if we're not controlling for these important omitted variables, our coefficients aren't really reliable for us to use as like causal, right? They're just evidence of correlations. And the next level, what you would do in like a 321 is you'd start to think about, well, how can I get at a causal relationship, right? And yeah, it's a lot more useful. There's a lot trickier, more difficult things though to make sure that you're getting a causal relationship. Yeah, notice I've got 86,000 observations. Like most of the time, you're going to be able to drive your p-values down pretty low. And it's the same idea, excuse me, that when we're looking at an estimate, right, for that slope, it should be centered around, that assumed true value of 0. Right? So if I'm thinking about my standard error, similar to when I had standard deviations for my sample mean, as that sample size went up, the way that the standard error is calculated, I'm not going to make you guys do it by hand, and Excel always gives it to us, so we haven't talked about it much, but it is also impacted by the sample size in a very similar way. So as my sample size goes up, that's going to drive down my standard deviations. My standard error really is a measure of like the standard deviation on those sample coefficients, right? So getting higher sample sizes greatly reduces that standard error so that we get a much more peak distribution, and we're guaranteed to see values that are closer to whatever the actual slope is, or in our situation, whatever the assumed true slope is. So when I'm seeing evidence out here, that p-value is going to be really, really close to 0, because if it's anything other than that 0 value, right, with 86,000 observations, I'm almost guaranteed that whatever that true relationship is, my sample slope would be really close to it, right? So if I see anything other than 0 with a sample size of 86,000, that probably means 0 isn't the true relationship. All right, any questions over anything? Yeah.
So even though the p-values that Excel spits out are 0,
Yep.
Would you want to say that with 100% confidence, or would you want to stick to something like 99?
We usually just leave it at 99, because you never truly have a p-value of 0. Like, right, technically, I switch it. Technically, this extends out to infinity, right? So I never can technically get a p-value that's 0. So yeah, we never stay with 100%. We always just kind of stop at that last level, which is 99. And sometimes people will say like 99.9. Yeah. Yeah, kind of the normal convention is you just stop at 9. I mean, what's the difference in 99 and 99.9? I mean, it is stronger evidence, but conventionally, like, they just kind of stop at 99%. Yeah.
So what is that, like 127 for the male?
Yeah, so if we're looking at these results, now how can we interpret this? Well, if we have a 1-0 variable, so right, male is 1 if the individual is male, 0 female, this would predict that if the lifter was male relative to female, holding all these things constant, holding constant body weight, age, the division there, or the type of this is like different equipment you could use when you're lifting, and age squared, obviously, if they're the same age, that would be the same. But if all those were the same, but one of them was male instead of female, the predicted weight lifted would go up by 197 kilograms across these 3 lifts.
Okay, so in that same column, sometimes it is a percent change, like how,
Percent
when is it,
change.
like you
Oh.
said it'd be like 12% on that other one.
Yeah.
So why is it sometimes like
Oh.
value and other times a percentage?
Yeah, so in this one, our dependent variable was like a continuous variable, right? It had units associated with kilograms. In the other example, our dependent variable was just a 1 or a 0. Was I promoted or was I not? So whenever I have this 1-0 variable as my dependent variable, now my coefficients represent changes in probability. So I might have been, I probably should have been a little bit more careful, but when I was saying like the probability decreases by 0.12, I could also say the percent chance that they get promoted decreases by 12%. The coefficients are always in decimal form, but, right, I think at this point, like if I see a decimal form, I know that I move it 2 places and I've got my percentage,
Okay.
right? Does that
Yeah,
make
it
sense?
does.
Yeah. Any other questions? These are all good questions. No? All right. Let me think if there's anything. Oh, I'll show you one more thing with this. So one thing I had thought about was maybe, and this is kind of a weird one, but we'll do it anyways. So maybe there's like a difference in like the intercept, but maybe also if I'm thinking about the relationship between body weight and weight lifted, maybe that varies differently for men and women, right? So what I could do there is create an interaction term. So maybe I want to get at something like this. So instead of like trying to identify differences across gender, maybe I just think, so kilograms lifted, maybe I think it's going to be, I think here we had male and body weight. But if I think that there's differences in the slope when it comes to body weight and kilograms lifted, right? Maybe I want to include this interaction term between male and body weight, right? So what I can do in order to do that is insert, right? Inserted that column in Excel and just call this male times body weight. And then I'm going to make it so we can see all these titles a little bit better. Okay. And just equals the male variable multiplied by the body weight of the individual. Now, if I get this to be a double kind of black plus sign, double left click, should do this for every single observation. Notice when I have a female lifter, the interaction term is just 0. Right? So now I could rerun this regression. And for my, oh, it switched a little bit because I changed. So I want to select total kilograms lifted. And then for my X variables, I'll include everything I did before, but I'll also include this interaction term between kind of male and body weight here. So select that, hit OK, got my results here. So we'll zoom in so we can see them. Okay, so still got really low p-values here. I can reject that, right? I can reject the null for all these and that they all have a significant relationship now. So if I'm looking at that male variable, notice now, just holding everything else constant, just the impact of being male is a little bit smaller than it was before because we're picking up more of that, the impact of body weight and being male, or the interaction term picks up some of that effect. So what I would interpret this as, you get really similar values, which is kind of crazy here. This is just happenstance, right? There's no reason why these should be this similar, but they are, just the way the data is. So how I would use this interaction term is I can say, what's the impact of body weight on the weight lifted for males versus females, right? So for females, the impact of 1 additional kilogram would just be, it would increase the total weight lifted by 1.66 kilograms. Right? So if I'm thinking about this here, if I'm thinking about the effect of a body weight increase of 1 kilogram, for females, that's just, whoops, the coefficient on that body weight variable, right? So 1.66. However, for males, if I think about if I'm trying to make a prediction, if kilogram goes up by 1, well, that would impact my predicted weight lifted here because this goes up by 1. So the weight lifted would go up by 1.66. But also, body weight would go up 1 here and the person's male. So 1 times 1, it would also go up an additional 1.66. So the total effect for males here would be what, 3.32? I would add those two coefficients together. Okay? So whatever group, right, is involved in the interaction term, the additional impact of a change in body weight here for males would be an additional 1.66 pounds lift. So this would kind of maybe tell us something like, for males, right, being much larger is impacting the way that they lift for whatever reason. There's structural differences in males and females or whatever it is, right? I'm not an expert in this field, but like for whatever reason, body weight seems to impact the amount of weight lifted for males more here than it does for females, right? And highly significant, right? P-value of 0. So I can definitely say that that estimate is different than 0. Right? Any questions over that? So kind of how you do that there is you can just include that interaction term between whatever that indicator variable is that you think maybe this X variable body weight, maybe it varies for males and females. So you take that indicator variable, multiply it by body weight, and then you just, where was this? I call it sheet 2. And then you just include that in your regression as well. Okay. Now, one thing I've never shown you examples of because you shouldn't do it. Anytime you include an interaction term, you have to include the 2 variables that you're interacting or you're multiplying, right? So if I want to include male times body weight in my regression, I have to include the male and I have to include the original body weight variable. If I don't, the results really mean nothing. Because if I don't include male here, but I include the interaction, well, now my interaction term is not picking up the effect of the interaction, but also the effect of simply just being male. Or if I don't include body weight, now it's including, the effect of male and body, but also just the general effect of body. So I have to make sure if I include that interaction term, I include both of the variables that I'm interacting in that regression as well. Okay. Any other questions? Yeah.
I have a question about the regression for the raw and the wraps.
Yeah.
So it's just kind of, it's confusing me a little bit because it would seem to me like the only way to lift in this instance is either raw or with the wraps. And yet both of them are negative.
Yep. So this takes a little bit more inside knowledge. So this was something that I had to leave a category out. So there's 3 divisions here. So you've got raw, wraps, and what they call equipped, right? So equipped lifting is like this crazy stuff that these people do where like they get these crazy tight suits that basically you put them under pressure and there's like a rebound effect. So like you're not really lifting all of the weight yourself, right? So the group I left out was this equipped. So what this is telling me is that if I'm using only wraps, so this is like wrist wraps, knee wraps they allow them to use, relative to these like crazy equipped suits, I am lifting about 100 kilograms less. And then relative to using these crazy equipped suits, if I'm just no wraps, right? Like raw is what they call like you can't wear knee wraps. I think you can wear knee sleeves maybe, but no wraps. Well, then I'm lifting predicted to lift about 135 kilograms less. So this is like almost like reverse telling you how effective these equipment suits are, right? Like, yeah. Now, if you wanted to, you could have left out like the raw category and then added wraps and this equipped lifting, and then that would kind of just give you the interpretation on the opposite direction. But still, it would be the exact same coefficients. They would just be positive because your comparison group would now be, the lowest instead of the highest. That's a good question. I forgot to mention that I left out that 3rd category. Any other questions on anything here? Is this stuff starting to hopefully I know we've got a couple different topics and things like that, but hopefully we're starting to see some. I think next week I'll probably do something similar and I'll review some like more quadratic and log stuff again. Because we didn't do any of that today. I kind of did like more of the indicator or using the dependent variable that's 1, 0. So it's almost like I'm going back to like that Monday before Thanksgiving and we're reworking all the topics we've talked about, but I'm just showing you more and more examples. Okay. All right, any questions from me before we get out of here? So that will be something I don't think you should have to do on the 4th Excel. You shouldn't have to move any of the columns around. Whereas that one thing I wanted to mention is the way I had it set up initially before I moved stuff around for the class today, I think I left like assistant and surgery off to the left. So those were like the 2 categories I wanted you to exclude. So I made sure I put them like everything was next to each other in order. And those 2 that you would exclude are kind of left on the left-hand side there. So you don't have to worry about moving the columns around. But in practice, you would have to do that if you're using Excel. That's why, if you kind of would continue to things in statistics, looking at linear regression, you would quickly want to learn SAS, Stata, R, some other program, because you don't have to like move things around to be in order or right next to each other. It can just do it like that. So, all right. I think that's all I have for today. We get out of here a little bit early. Yeah, I'll next week we'll just keep going through a few more examples and then probably start some review as we get towards the end of next week. We'll use that Monday of finals week to do more review as well. I think our exam is on Friday, unfortunately. That's the time block that it's set for. So I've actually got 2 exams on Friday this semester, so I lucked out. But that whole week, I'll be around. And if you have questions during the week, feel free to like set up a time. My office hours, I mean, I guess they'll be the same. I'll probably be here during those hours, but you know, it'll be a little bit different that Tuesday, Wednesday, and Thursday. So I would suggest maybe shoot me an email so we make sure we can set up a time so I know that I'm in my office when you want to be there. Okay. All right. All right. I will see you guys on Monday. Have a fun, safe weekend. Emphasis on safe.
In person test.